Hello everyone, and welcome back to another cooking session here on the Codesultant Channel. In our last episode, we didn't just look at table 220.55. We laid out all the ingredients on the counter. We chopped through the appliance types, mixed in the columns, sprinkled in the notes, and uncovered the NEC's recipe for diversity. Today, we're turning up the heat. In this session, we'll focus on one essential ingredient that often gets misunderstood. Note 1, and how it connects to branch circuit rating and conductor sizing. This is where many designers have made mistakes. We'll walk through real-world examples to show how Note 1 guides us when dealing with ranges over 12 kilowatts, and how to avoid the common trap of jumping to the wrong column. So let's roll up our sleeves and step into the kitchen of code. Before we dive into the notes, let's pause and clear up one of the most overlooked ingredients in this table: the branch circuit rating and conductor sizing. It often starts with how we interpret the table's title. Here's how the NEC phrases it. Let's read it closely. Table 220.55. Demand factors and loads for household electric ranges, wall-mounted ovens, counter-mounted cooking units, and other household cooking appliances over 1 3/4 kilowatts rating. Column C to be used in all cases except as otherwise permitted in Note 3. Now let's simmer on that last line for a moment. Column C to be used in all cases except as otherwise permitted in Note 3. That's not just a little note in parentheses, it's a key detail. It tells us that column C is the default for all calculations, unless Note 3 specifically allows us to season the recipe differently. This single line is the turning point that determines whether we size directly from column C or apply an exception. And what better way to start than with a real-world example, one that trips up even seasoned designers. Suppose we're dealing with a 5 kilowatts, 230 volt, single-phase household cooking range. What should its branch circuit rating and conductor size be? Here's where many designers have slipped. We see a small appliance, say a 5 kilowatts range, and instinctively jump to column B. It feels logical. Smaller load, smaller column. But unless Note 3 explicitly permits it, column B is not the right choice. The title of table 220.55 makes it clear. Column C to be used in all cases except as otherwise permitted in Note 3. Misreading this clause leads to undersized conductors, incorrect breaker ratings, and ultimately, non-compliance. So let's walk through it properly. We start with column C. That's our default. Then we check Note 3, which gives us a very specific permission. In lieu of the method provided in column C, it shall be permissible to add the nameplate ratings of all household cooking appliances rated more than 1 3/4 kilowatts but not more than 8 3/4 kilowatts and multiply the sum by the demand factors specified in column A, or column B. In simpler terms, if you have multiple appliances, each rated above 1 3/4 kilowatts but not more than 8 3/4 kilowatts, you're allowed to use column A or B, but only if you follow the method in Note 3. That means, you add up the nameplate ratings of all qualifying appliances. Then you apply the demand factor from column A or B based on how many appliances you have. If your appliances fall under both columns, you split the group, apply the correct factor to each, and add the results together. But here's the catch. Note 3 doesn't apply to a single appliance. It's written for multiple units. So in our example, 5 kilowatts range, Note 3 doesn't give us permission to use column B. Instead, we go back to the rule in the title. Column C is to be used in all cases. But there's one more twist. It tells us that for a single appliance under 12 kilowatts, we can size the branch circuit directly from its nameplate rating, no demand factor applied. So for our 5 kilowatts range, we treat it as a full 5 kilowatts load. Let's do the math. Rated current is equal to 5,000 kilowatts divided by 230 volts. This will give us 21.7 amperes. That means we need a number 10 AWG copper conductor and a 30 amp breaker. So the takeaway is this. Column C is your starting point. Note 3 only applies when you have multiple appliances within a specific range. And for a single unit under 12 kilowatts, you size it directly, no demand factor. And remember, table 220.55 is primarily a multi-appliance demand table. Its real strength is in service and feeder load calculations when 2 or more appliances exist. Columns A and B come into play when multiple appliances are present, when Note 2 applies, averaging unequal ratings, or when Note 4 applies, treating groups of small appliances as one range equivalent. Now before we go further, let's clear up another common question that often comes up when applying Table 220.55. Why are we using kilowatts and not converting to kilovolt amperes? Is it okay to just stick with kilowatts? The answer is yes, and the NEC itself confirms it. Section 220.55 states, kilovolt amperes shall be considered equivalent to kilowatts for loads calculated under this section. That means for household electric ranges, wall-mounted ovens, counter-mounted cooking units, and other household cooking appliances rated over 1 3/4 kilowatts, we are permitted to use the kilowatts rating directly when applying Table 220.55. Why? Because these appliances are primarily resistive loads. Their heating elements operate at or near unity power factor, so the real power, kilowatts, and apparent power, kilowatts, are essentially the same. The NEC recognizes this and simplifies the calculation by treating them as equivalent. So unless the manufacturer specifically lists the rating in kilowatts, which is rare for household cooking appliances, you do not need to convert. Just use the nameplate kilowatts rating as is. Let's take another example, this time with a larger appliance. Suppose we're asked to size the branch circuit for a 15 kilowatts, 230 volt, single-phase household cooking range. Before we jump into the calculation, we need to understand how Note 1 of Table 220.55 applies. Note 1 states that for ranges individually rated more than 12 kilowatts but not more than 27 kilowatts, the maximum demand in column C shall be increased by 5% for each additional kilowatt, or major fraction thereof, by which the rating exceeds 12 kilowatts. This means that although column C sets the base feeder load at 8 kilowatts for one range, we must adjust that value upward when the range exceeds 12 kilowatts, and that adjustment is exactly 5% per kilowatt over 12. Applying this to our example, we subtract 12 kilowatts from the 15 kilowatts rating, leaving an excess of 3 kilowatts. Multiplying this by 5% gives us 15%, which we then apply to the column C base value of 8 kilowatts. The adjusted demand becomes 9.2 kilowatts, which at 230 volts translates to about 40 amperes. Therefore, the appropriate overcurrent protection is a 40 amp breaker with number 8 AWG copper conductors. But here's the important question we need to ask. Why do we apply a demand factor in this case, when earlier we didn't? The answer lies in the NEC's distinction between branch circuits and feeders. For most branch circuits, you size as directly from the full nameplate with no demand factor, which is why in our earlier example the branch circuit carried the full combined load. However, when a single household range is rated over 12 kilowatts, the code recognizes that it is unlikely to operate continuously at full load. That is why Note 1 of Table 220.55 allows us to adjust the demand value, starting with column C's 8 kilowatts and increasing it by 5% for each kilowatt above 12. And here's the key clarification. The NEC explicitly permits using Table 220.55 for branch circuit load calculation for one range, stating that, calculating the branch circuit load for one range in accordance with Table 220.55 shall be permitted. This is the one exception where a demand-adjusted value can be used for a branch circuit. Everywhere else, demand factors are reserved for feeders and service calculations. In summary, the branch circuit sizing for the 15 kilowatts range based on the full nameplate is about 65 amperes, requiring a 70 amp breaker and number 4 AWG copper conductors, while the feeder or service sizing using Note 1 adjustment is only 9.2 kilowatts, about 40 amperes, requiring a 40 amp breaker and number 8 AWG copper conductors. The takeaway is simple. Branch circuits carry the full rating, feeders benefit from diversity, and Note 1 tells us exactly how much to add to column C once the range exceeds 12 kilowatts, and in this one special case, the NEC allows us to apply that adjustment even to the branch circuit. Now, just like in cooking, another question often comes up when we're preparing this recipe for compliance. Can we combine multiple household cooking appliances on a single branch circuit? Like leaning several pots onto one burner. It's a detail that deserves careful attention, because the code has its own rules about what can share the same kitchen space, electrically. See you in part 3, where we'll lean into this question and continue applying the remaining notes of Table 220.55, making sure every ingredient is measured correctly and every step of the recipe is followed. Thank you for watching my video. I hope you enjoyed part 2, and I look forward to cooking up more code clarity with you in the next session.